have your attention, please come in. Could some of our colleagues spread the word to the hall? We have a couple of fabulous speakers here. Just because it's the end of the day, we don't want to have you shortchanged, and we certainly don't want to have the speakers shortchanged. All right? I know there's some high-level business going on out there. We'll have to, some of this high-level business, which is part of the reason why we have this conference, may help us all. All right? Okay. I would now like to introduce a contributing editor of our magazine, Mr. Chris Tinsley from Nottingham, England. Chris has been in contact with Jed Rothwell and I continuously since around 1991, more intensely in 1992 and beyond. We've had many extraordinary adventures together in the cold fusion war, which it really is, of course, because obviously we don't see the New York Times here today. Obviously they should be here. Although actually, to think of it, we didn't invite them. But, no, actually we sent them a notice. But in any event, Chris has had many adventures in trying to get to the bottom of very anomalous claims, such as the infamous or famous Potapov device from Moldova, which he's going to talk about. We featured that in the second issue of our magazine. I did very serious, big-time plumbing operations with my colleague Jeff Driscoll, who has been taking your money today, and last summer. Nearly killed ourselves doing it, or mainly the work of Jeff. Hot and sweaty. I couldn't do it all myself, but he sure as heck did a great job. We proved that at least under the conditions that we had in our laboratory in Bow, New Hampshire, we could not see excess heat. Not to say that somewhere in the wilds of the former Soviet Union, or Moldova, it doesn't exist. We still hear reports from the highest levels, as Chris will tell you, that there is positive results. And only the other day did I hear a report from Massachusetts of a device that we may yet get to test again, which has some very serious anomalous properties of water coming out of it. That's the claim anyway. We'll be looking at that. We'll be looking at many other things. Bottom line on Chris Tinsley's talk today is we are the action team that goes to the site of the latest reports of anomalies and tries to find out whether they should be brought into the fold or thrown in the trash can. So now, without further ado, let's have Chris Tinsley. He's an electrical engineer, by the way, many years in the computer field in England, working for Marconi and many other fantastic companies doing military radar research and many other things. And he's the best electronicer I know. Take care.
Well, after all these excellent presentations, get a bit of intellectual life relief.
Are you above? Is he?
Can you check, make sure it's on, Gene?
Let's check the button. He's a good electronicer, but he may not know how to turn the on switch.
Oh, there's using switches then. Much too sophisticated. Is that better? Good there.
Right. Well, as I say, after all these fine presentations, you get a bit of intellectual relaxation now because I'm not going to be communicating anything of great significance. As Gene says, Jed and Jed and Gene and I have worked together for several years now. Initially, I was working really on things like persuading the BBC to run that, to make that documentary we saw at lunchtime, or some people saw. And latterly, I've moved more into experimental stuff. Now, some people have all the luck. You see, now, Jed Rothwell, all he had to do was go over to Anaheim, get his shoulder between the guys who were standing in front of this thing, and get in there with his thermometers and so on, and, you know, and do a lot of hard talking, and they let him measure it. Funnily enough, having grudgingly let him measure it, they're now passing out his report. But, you know, that's life in this business. One of the things that came out of Jed and Gene's visit to Hydrosonics was the suggestion, even at that stage, and I'm sure Jim will recall, Jim Griggs will recall, that we had a possibility that there was a cavitation effect. Even at that time, it was beginning to be thought that there was a cavitation effect. Certainly, Dr. Puthoff feels that a collapsing microbubble will, is one way in which the zero-point energy, so-called, could be tapped. And there were good feelings about this kind of device, a device that provided cavitation. When at the 5th International Conference in Monaco earlier last year, there were reports of this remarkable machine in Russia, which would have an advantage over the hydrosonic pump of being very simple and having no moving parts and effectively consisting of a stovepipe. We thought it would be a good idea to try and investigate it. Now, my investigation may very well turn out to have been just wholly misleading, and it's perhaps an object lesson in how confusing things can be. We're still not certain the device doesn't work. What we are certain of is it is no longer worth the kind of effort we've tried to put into it to find out whether it does or not. The most positive reports we've had are from people as prestigious as Energaya, who are the people that make all the big boosters for the Russian space program, confirming the over-unity performance at about a ratio of 1.7 to 1, which is, you know, pretty damn good. And to be fair, some later tests I managed to organize in St. Petersburg converted one excellent physicist there, who was a former advisor to President Gorbachev, and highly skeptical, but was very helpful to me personally. He helped arrange these tests, and he now feels, reversing his original position, that the device does produce over-unity effect. All it is in effect, really, is a tube. They come in different sizes, where a vortex is initiated in this pipe by a chamber with vanes inside it, and this vortex travels up the tube. The idea is that microbubbles, cavitation bubbles, will form actually inside the liquid, just as Mr. Griggs said, and would then produce this over-unity heating effect, and the vortex was then broken by a spoiler plate at the end of the tube, and out it would come. Now, when I first went to see the inventor, one Dr. Potapov, with a good friend of ours who is a chemist in Romania, a Dr. Gluck, who also speaks perfect English and Russian, which is very, very helpful for translating. And I must admit, I came away with a good impression. Now, I'm going to play a short section of the film I made in just a moment, Jean. I should explain here that these field trips are not the sort of thing one might imagine, where one flies to a laboratory and people all get together and seriously discuss what they're going to do and take measurements. It's actually more like it is on the tape here. And this tape is going to make me look ridiculous. I don't mind that. But in my defense, I have to say that I'd flown to Bucharest and then got on a train which took 14 hours to get to Moldova. And since the railway gauge changes at the border between Romania and the old Soviet Union, they have to lift the carriages off one set of bogies and put them on another one. And I'd been told I didn't need a visa, I could buy one at the border, so I had these large ex-Soviet goons leaning on me about why I hadn't got a visa. And we'd just been treated to lunch by Dr. Potapov, and I'd been, against my will, forced to consume about half a bottle of Blue Absolute vodka. So this is the sort of preamble to... Well, he did say, you know, I heard them saying, and it's easy enough if you listen to what they say, no matter what the language, these Englishmen can't hold their liquor, because I wasn't drinking very much, you see. And I had to explain that even though I don't like the stuff, that any Englishman can drink any 12 Russians under the table. And of course, one thing led to another, but this is what happened. This is me coming into the Institute of Physics in Chisinau, Moldova. There's no sound.
We get the sound?
Experimental, I suppose, okay, I'll go on now. This is the entrance to the Physics Institution, and as we come into the corridor, you can see all of this, but all along here, endless rows of Yusma machines. At this end it's very dark, but perhaps you can see them all. Astonishing. That's Peter and Yuri at the other end, looking at them. I'll walk along the slide. Most expensive confidence trick in history. And so it goes on, back into the darkness. Anyway, this is the Institute of Physics where we're hoping to do these tests. I'm looking forward to doing it. The idea is that we'll have a very large tank of water and be able to measure the COP using the temperature rise of a very large volume of water. I'm looking forward to this. I'm concerned that I'm concerned about measuring input power. Input voltage is easy. Input current may be less easy. I have a Beckman multimeter with me. I don't see a big problem. I'll see how I get on. Apparently this is a shipment of 200 machines for Russia. The difference is that these include the pumps and all the rest of it, and the motors. Whereas our machines will simply be the bare machines, and we've been told a great deal about how we're going to have to match the pump correctly to the machine, and Yuri's going to tell me all about how to do this. Right, we're inside the experimental workshop now, and I hope we're going to do some sort of picture that's a bit mixed up. Those are some, but what you can see now are the radiators for this particular machine that's installed, and it is connected to this Yusma machine. How many radiators? How many? 16. 16 radiators. is a practical system set up here for heating an experimental workshop. Now, they have told me the volumes of water, and they have measured how long it takes to heat up to an indicated, you can perhaps see there, that the button is set for 50 degrees. And sure enough, it cut out after that time. However, although I can feel that the temperature of the water, which is measured from this thermocouple down here, there, although I accept that this is probably perfectly accurate, and they have told me the volume of water, they have offered to drain all the water and find me a resistor so that I can measure the current. They have no oscilloscope, so I can't measure the phase angle between the current and voltage. It is, I'll check in a few minutes what the power of the pump is. I think it's 4 kilowatts. As you see, it's stopped now. However, I have said that although I can take these figures, to me they mean nothing. I do not believe it's possible in this environment. You see, this is a workshop. I mean, this is a crazy situation. I cannot accept any of their figures. I cannot accept the volumes. I cannot accept the power of the motor. I have brought a digital voltmeter with me to check voltage and current, but it simply isn't practical. I am far more convinced by the large number of machines being sold, and what I want to do now is to go on and discuss with Yuri and with Peter the best protocol for driving these machines as well as possible. I think the whole idea of making a sensible test is absurd. So I'm going to cut here. The battery's a bit low anyway, and we'll go on from here and discuss how best to drive the machine.
Well, you get the idea. It isn't that easy, and you get cultural differences, and you get that kind of mess where they assumed that I would, as I was saying on the tape, and you could hear it over that they expected me to accept the volume of water being heated. They expected me to accept their thermometers. I think they wanted me to accept the numbers stamped on the electric motor as being the amount of power the thing was taking. And I obviously refused. I mean, you know, we're not exactly a bunch of wide-eyed idealists, as I'm sure you've realized from Jed's talk. However, the problem was that they're selling these things by the thousand. And Gaia says they're 1.6 times unity in their performance. But of course, the guy who runs the company was happy enough to sell us some of the basic tubes, but the fact is that when we tried to run them in the way that we were told how to run them while I was there, they don't work. Now, there's diminishing returns. You can put all the effort you like into these things, and maybe you'll eventually get to the bottom of it, but it simply isn't always possible to get to the bottom of it. And in a sense, it was a valuable lesson, because you know, as I'm sure Mr. Griggs would agree, that getting the parameters right on any fluid device is not as easy as all that. And whereas with electrical systems, you can see what's going on much more clearly with oscilloscopes and the like. You can't do that with the other things. So that was largely the story of that machine, and a rather sad story it is. Yes, Jean's also asked me to mention this business of the SciEx scooter that we heard about from Hal Fox a short while ago. This is another interesting case study, if you like. I attended a meeting at the house of the UK representative of SciEx, where Mr. Takahashi also turned up. And they had this scooter. It's a very heavy thing, that scooter. I can scarcely lift one end of it. It's very massive. And it has a little tiny motor on the back, about so big, and it has 4 lead-acid 12-volt batteries, which I suppose must be about 20 amp hours maximum inside it. Somebody asked what this thing was. This is the crash helmet. It's a modified Taiwanese scooter. I thought it was Honda, actually, but it's not. It's Taiwanese. The motor is, I think, on the other side. You can't see it in this drawing, in this photograph. The batteries are arranged along here, and in the storage compartment here there are a few capacitors. There's nothing exotic about the capacitors. They're perfectly conventional electrolytics. So I asked if I could take a ride on this scooter. So to my surprise they said yes. So I disappeared into the wilds of North London on this thing. I will say its performance was very, very striking. There's a steep hill outside the house, and I rode it flat out up this hill, and I got it up to 50 miles an hour uphill, 70 plus kilometers per hour. And their boast that it will do, that's with me on it, and the enormous weight of the thing itself. And I well believe their claim that it will do 70 miles an hour on the flat. I hammered it around North London for 25 minutes, trying to be as unkind to it as I could. In other words, I was violently braking and accelerating as much as I could to, you know. And by the time I got back, the brakes were both pretty hot. But the motor was genuinely completely cool to the touch. So we know it has to be a very efficient motor. I also measured the voltage across the batteries, and each of the 12-volt lead-acid jelly batteries was giving, that's not it, gel batteries you'd call them here, wouldn't you? Gel batteries was showing 12.85 volts. Now, that struck me as being a bit peculiar because, I mean, we are talking about, I was pushing that motor at kilowatts, and 4 little 12-volt batteries. Now, I didn't feel too good about this. I tried revving it up on its stand, and I determined that it's regenerating. In other words, when you twist the throttle right back, and the thing slows down, that it will start to partially recharge through regeneration. However, as I say, the brakes were hot, and so on and so forth. Now, subsequently, there's been a few weeks later, there was a report in the London Sunday Times about this. And I must admit, I found it extremely funny, because the man was saying that this had a range of 500 miles, and he said that this had been achieved by improving the performance of the electric motor. Now, an electric motor, just in case anybody doesn't know, of the sort you're going to put in here, which would be a DC permanent magnet motor almost certainly, in fact I can't imagine any other kind that would suit the job, is going to be running at, well, certainly in excess of 70% efficient, shall we say. There is no slack. There is no way you can make a very, very significant performance improvement to an electric vehicle by working on the motor. The Sunday Times said, well, of course, everybody's been concentrating on the batteries and nobody's been concentrating on the motor. And frankly, anybody who knew what they were talking about, who read that report, would see that it was shrieking of an over-unity claim all the way through. In fact, Takahashi said to me, I said, you know, because I don't mean I believe this. What I mean is you have to ask the appropriate questions. One of the questions I asked was, will it run indefinitely? And he said he said, well, he's got graphs that claim it do it by implication. He said, on the flat it might at a reasonable speed. He said, but the motor is not sufficiently efficient to allow it to run under normal circumstances indefinitely. I said, are you claiming over unity? He said, no. He said, he's a cunning old chap, I will give him that. He said, we believe that the magnets will lose their performance over at about 3% per annum, and that is supplying the energy. So I said, no, it isn't. But anyway, we decided to disagree on that one. So then he showed us. By the way, I would reckon, to be fair to all this, you would have to have an electric motor of something, I would guess, and anybody willing to argue, at a guess figure, somewhere between 500% and 1,000% efficient to be able to run indefinitely under these, under any kind of traffic conditions. I don't know if anybody would disagree with that, but I think it would have to be about that sort of thing. Somebody's nodding, that's great. Okay. So then we saw a video which hadn't been made by Takahashi, it had been made by somebody else. They revved one of these motors up, disconnected the batteries, and it was left driving via a very floppy and very casual looking plastic V-belt. It was driving a small conventional alternator, which was driving two 60-watt car headlamp bulbs. Well, that tells us one thing. It tells us that the device is either real or it's a fraud, because it cannot be a mistake. I mean, if you have an electric motor running apparently indefinitely with no input, and you put the, and it's driving through a floppy V-belt, it's driving an alternator, and you're driving two car headlamps off at 120 watts or something, then it will stop immediately. If it goes on running, then you know, either there's somebody underneath turning the handle, or it works. Okay. He then showed us some watches, which he said were running with no batteries, and they were completely transparent cases. And to be fair, you couldn't see a battery inside them. He also showed us some other devices, like, for example, this capacitor that's been alluded to, 20 farads at 25 volts in less than a cubic centimeter. And we saw his resume. Well, his resume, he was working in a senior capacity developing things for Sony for many years, including the Betamax system. He's done a lot of work on magnets. He had these hysteresis diagrams, which Hal Fox has showed us, which indicated that they had, the easiest way I find to characterize them is a 3 Tesla surface field. 1 Tesla is 10,000 Gauss, and the best magnets I've ever laid my hands on, and which have torn skin from me, they're violent, nasty little things. The very powerful neodymium iron boron, the best you can get is about between 1 and 1.2 Tesla. So he has something pretty strange there, he claims. But then you see, over the last few days, we've heard that the first tests, completely independent tests on these magnets have been underway in this country, in fact. And all the indications are that those magnets are exactly what they claim to be. So it's an open question at the moment, but I mean, it's not like somebody wandering out of the backwoods with claiming he's got a perpetual motion machine. In fact, the guy is very carefully not claiming perpetual, you know, over unity now, unless you study it carefully. And I honestly think it was the kind of reception that we gave him to it. So I always try to be cautious. He didn't get the best reception in England, I think, for these claims. In fact, I would go so far as to say they went down like a rat sandwich. People just didn't like them. And he's kept quiet about that. But we do know that a set of these motors are being made. We also know that he wants to attract capital for manufacturing these tens of millions to manufacture these magnets in England. Now that might seem a bit strange, but that again makes sense because there's very little venture capital available in Japan, and any Japanese who wants to make anything, for some bizarre reason, comes to either England or Wales, and where we all seem to get on very well with the Japanese, and they get on well with us, and they like it, and they have their kids winning the cultural festivals by composing poems in Welsh. I kid you not. And this is not standard operating Japanese practice, that, you know, if you want to make something, you want some capital, you go and build it in England. So he's planning to make his magnets in England. Now, I had a theoretical, you may laugh, but I had a theoretical objection to this scooter. I don't know which, I think there's the, I think the motor's on that side. It's back to front, so it's on the other side. See if we can see it. No, they've photographed it in each case from the wrong side. Not to worry. It's just a little motor. It can't possibly work. Why can't it possibly work? Because the magnets have nothing to do with it. A conventional electric motor operates absolutely in accordance with well-known energy transfer equations. There's no question about it whatsoever. So it can't work. I've had some experience playing with these things myself. I've had an electric motor, and I don't care what anybody says, I saw significant over-unity out of it. I then set to work and got rid of all the little mistakes and the losses and all the rest of it. I really felt I got a handle on it properly and so forth, and fancy that, it stopped doing it. And every time anybody's had anything that does appear to work, it's turned out that the motor is non-linear. In other words, if you like, there's a step as it goes round, or it flicks suddenly from one state to another as it goes round, or it's pulsed by a square wave or something which makes it behave in a non-linear manner. And this one couldn't do. And then the penny slowly dropped, and I was speaking, I've forgotten who it was now, spotted it. Oh yes, Mr. Rose spotted it instantly. What is non-linear about this motor? The answer is very simple. Those magnets are 3 Tesla, or claim to be. The saturation flux density of iron is only around 2 Tesla. And if you have those kind of magnets in iron armatures, which is what the drawings show they have, then that motor is non-linear, because it is going to go through peculiar transformations as the iron saturates and unsaturates as the rotor goes round. So in that sense, I suppose it raises the thing's credibility. An intelligent, competent guy, a good engineer who can build a machine like this, who has got a lot of products under his belt, who has this amazing magnet, nearly 3 times the power of anybody else's, and which apparently is nearly 3 times the power of anybody else's. So when somebody phoned me on behalf of a well-known physicist who he didn't wish to name and said he had an electric motor which would run with no input power and drive a 3-kilowatt generator, I said, a rotary device? And he said, yes. And I said, it's an electric motor which is non-linear. There was several seconds silence, and he said, how did you know? And I said, what are your plans? He said, well, we're planning to keep it under wraps for a couple of years while we iron all the bugs out of it. And then we're going to, you know, bring it out to the adoring public, and we're going to get a Sir somebody to go out and double check that this motor performs in the way it does and write a scientific report which everybody will accept. And I said, forget it, because I take exactly the same line as Jed Rothwell in these matters. You know, I mean, this is the classic example of inventor's disease. They want control over the process, they want to direct the whole thing, they want to maintain secrecy, they want to leak a little bit out to people like me to see what I think. They want the penny in the bun, they want their cake and they want to eat it as well. But to be fair to Takahashi, he's only been in this game a very short while, and I think he's a lot sharper than the rest of them. So if he's got something, I think what he would do, and what I think he's doing, is to ride forward on the strength of the fancy magnets, which he apparently does have, and quietly slide this in through the back door afterwards. But I believe he wants the Nobel Prize as well, which of course is always, he wants the praise of the scientific community or something. You know, why people can't just be contented, you know, with a villa on the south of France and be able to tear up £5 notes the rest of their life and never worry about it. I just don't know. I mean, they want to win prizes as well. Moving on from that, I'm taking my cue really from Hal Fox's splendid presentation about the work of what he refers to as the Cincinnati group. Again, we heard this story relatively recently, and to say we were enthusiastic would be to exaggerate, really. The collection of claims was just the kind of thing we didn't really expect to hear. But then Gene went to Cincinnati. He came back with a videotape, which didn't impress Jed Rothwell at all, which I didn't see because we have the problem of the different format in the UK. We can never afford to translate the tapes. But this group was amazingly open, friendly, and straightforward. And despite the fact they hadn't even got all their applications in at the time, they sent me samples and supplies of materials to try this experiment out myself at home, which I did. But I had a bit of a problem because one of the electrical devices I was using wasn't big enough, and it would have cost me several $100s to buy a bigger one, so I didn't. But I did use a bit of electronic trickery to build up some more equipment, and I had replicated this thing. I'd seen it happening, but you know, the smoke was pouring off the other end of the bench while it was happening, so I really had to give up. But I brought my equipment to Gene's house, and where he had an enormous one of these electrical devices we needed. And a couple of days ago, I had the pleasure of seeing Jed Rothwell jump a foot into the air and come down squawking like a chicken when he saw it go. Here's an example of the sort of thing you can do. Now, it's not terribly plain, this, but I've actually got the bits in my pocket. There's one of the bits. I'll walk up and down with it. This is an ordinary quarter-inch ceramic tile, and if you look, you can see that it's actually been melted right through in well, next to no time. And the blue glare and and we weren't putting much power into this thing, I tell you. We weren't putting much power in at all. We have been told, and I believe it, that if you put a oxyacetylene blowtorch up against a quarter-inch tile like this, it is going to be a very long time before you're able to melt a hole clean through it. It's not easy. This thing, you know, this thing melts asbestos like chocolate. It does a lot of very remarkable things. We haven't done any calorimetry on it yet, sadly, because of these practical difficulties I mentioned. And in 48 hours and trying to get ready for this conference, we didn't have time to even dream up a calorimeter. But it was certainly an astounding thing to watch it happen. You're surrounded by blue light when it's running. I mean, this is hot. with a very small power input. So something strange is happening there. We know that this particular process has been tested in a kind of wind tunnel calorimeter, if you can imagine such a thing. An airflow calorimeter sounds better. And apparently is approximately 10-to-1 over unity report. Now, I can't comment on that. I understand that some people have, it's easier in some ways to test their claims to accelerate the decay of thorium from billions of years down to a few minutes and produce the same daughter products. In some ways, that's an easier thing to test for than to test for the calorimetry of something like this. But there again, something which started off, which we viewed with very little enthusiasm when we first heard about it, the combination of the openness and helpfulness of the principals of the Cincinnati group and their help in helping us to do this, which is very easy if you use the right materials, and will not do anything if you don't use exactly the right materials. The specificity of the process and their apparent lack of desire to win the Nobel Prize and so on and so forth, you know, we warmed to them very strongly, and I join with Hal in recommending anybody who wants to get on the ground floor of a new process to look very carefully at what this group is doing. We can, of course, put any interested parties in touch with the group. Good, I'm running out of time. One other thing I want to say is this, that I admire the work the scientists are doing in this field. I think it's very brave of them. I remember when I was talking with Dr. Greneau, who's here, and his son at Oxford University, and Dr. Greneau Jr. Felt he had to close the door before talking about some of his work. This is, if you imagine a bastion of intellectual freedom, you'd have thought Oxford University would probably be it. But even there, it's not, apparently. So I admire these people, but I have one thing to say, and I think Jed feels it even more strongly than I am. I find the science very interesting. I find it intriguing that these sort of effects occur. I find Mr. Griggs's blue steam and SETI's blue glow and all these other things quite fascinating. But in one sense, we haven't got the time for science. When I said that I refined what appeared very clearly to be an over-unity motor out of working properly by bringing it back into conventionalism and stopped it working. Now, in one sense, I have to say that at the moment, much as I admire the scientists, in a sense we don't have time for the science. Not yet. For one thing, we have, I'm sorry, you know, I appreciate a lot of people won't agree with this, and I support this work, but most of us, I think, are going to have to concentrate on bringing, on opening up the field, trying to help the inventors lose what Jed so well described as this own worst enemy inventor's disease problem, where they all think they've got the Holy Grail, like these people that telephoned me, and they don't realize anybody else is doing it. I had to tell him I was riding around on one of his electric motors a couple of weeks previously. There's a horrible level of pragmatism required in all this. If you get rid, I mean, for all I know, if SETI get rid of all the lumps and cracks on their beads, the thing may stop working. It may be the cracks that are making it work. I mean, it is a very Edison kind of situation where people are going to have to be a bit pragmatic. And in a sense, the more you study the subject, the more likely you are, in a sense, to be trapped back into conventionalism and lose this, this strange effect. That's not to say you haven't got to be rigorous and careful in your measurements and so on. All those things still apply, but somehow or other you've got to decouple your creativity from your schooling in conventional knowledge. I don't think at the moment, I think we have to concentrate on the immediate reality. There'll be plenty of people queuing up to investigate these machines. Somebody once said that scientists will believe anything they're funded to believe, which is perhaps a trifle unkind, but it is true that if, for example, shall we say, the SETI device or the hydrosonic pump present completely unavoidable evidence to some people, then there are people part of the way up the funding tree who are going to say, we want to know what's happening, we want to know why you get this effect at a very low temperature, and yet other people can do something which resonates with it at a very, very high temperature. They're going to want to know the answers to these questions. And until there are people standing there with their wallets open saying, this has to happen, we've got to get to the science of this thing, then for the moment I think the wallets really need to open to get the thing out into the field. And Jen and Jean and I try very hard to take a straightforward practical attitude to life and to be willing to go out and examine machines no matter how dubious they are, and within our funding limitations and so forth, which are very severe, we do our best. And I very much wish we could do more, but we are very limited in what we can do. Well, that's about it. I've dribbled on long enough. Has anybody got any questions at all?
Just one.
Yeah.
On the motor, you spoke about the magnets on iron core.
Yes, they're set into iron armatures.
Should they use like neodymium iron boron and make that as a coil and use the shock system?
No, these are solid blocks of their new magnet material.
Well, Christopher who's here says that we can't believe that Energia is behind it, and we can't get to the bottom of it. Well, they have a report with some numbers, but these numbers are not good enough for us. You know, and we would like to have, it's a shocking claim, and we wonder why we ourselves can't do it.
I spent a week in St. Petersburg trying to go through all the official Russian channels. We've got business contacts in Moscow, we've got science contacts, we've got people who used to work there at Gaia, and we still didn't manage to get to the bottom of it. It wasn't for lack of trying, believe me.
There has to be, let me just make...
That's why I went the second time, because I knew we could do that. It didn't work.
There are many instances that I have observed over the last number of years, which if we had had the proper, well, let's put it bluntly, funding, okay, to go where we had to go, do what we had to do, call what we had to do, spend the time that we had to do, we could have got to the bottom of it. I'll give you a classic example. We didn't show it, but Stan Meyer with his water tower, with his umpteen patents, his various theories of things and so forth. I was in his lab. Jeff Driscoll back there was also in his lab for a day. Okay, and we saw this amazing effect, astonishing effect of apparently a stoichiometric mixture of hydrogen and oxygen being formed amazingly quickly in a water tank. Okay, we saw no possibility.
And it stayed cold? Yeah,
it stayed cold, but we didn't have the thermocouples there and so forth, and we didn't have the time to, in the case of Mr. Meyer, to flatter him for a week, which is what you'd have to do, in order to get the key measurement we needed, which was the current in the wire. If we had the current in the wire, we'd have been able to prove that he has what he likely has. But for all practical purposes, he has nothing, because he's talking about billion-dollar deals that he's rejected with the Arab countries and this, that, and the other thing. And you know, it's just impossible. You have to have a concerted effort. That's basically the bottom line. Could we hold? Yes, yes, Keith, and then we'll go on because Paul Violet wants to say something. Go ahead, Keith.
Yeah, just a comment. Hello, Chris. We talked by telephone.
We have indeed. We have Les Johnson. It's nice to meet you.
Lots of nice tapes, which I.
Yes, you've helped out a great deal with this terrible tape incompatibility problem. Thank you.
Just a comment about this melting experiment. We've worked on a theory of melting, which is based on it's kind of an inverse of this Young-Teller business that I was telling you about before. And the idea basically is that when something melts through applying heat, basically what you do is you alter the interatomic distance between the atoms and you cause bonding levels, which are filled, and antibonding levels, which are empty, which are responsible for the long-range correlations, to cross. And there's some experimental verification of this in various materials, and we've been able to calculate the melting temperatures and so on. Now, another way of transferring electrons effectively into antibonding levels is perhaps by this charge cluster. In other words, if indeed you're producing large clusters of electronic charge, and they are delivered locally into the ceramic material, into these antibonding levels, then you can melt the material just by direct electron transfer. And that's
I'm not denying it.
This is just a suggestion of how this may work.
But there certainly was most intense heat. The light coming from this melt is blue at the beginning.
And the quartz, I might say, we'll just go on and get all the violet up here. Then we'll try to open it up at the time that we have left.
Yes.
In the quartz, we saw the most astonishing, what I would call little fireballs moving. They were just little plasma balls, I might say. They were moving around. I don't think I was, for about 10 minutes or so, I wasn't imagining. They were moving around inside the quartz. It was most remarkable. One thought of ball lightning, of course, which is said to go through things. That was in that quartz, as far as I could tell.
Yes, I must admit, it's the single, and I think Jed would agree, it's the single most dramatic, shall we say, what would we say, unconventional experiment I think any of us have ever seen. Okay, could we hold to the questions after? We'll try, because Paul Violet has come a long way. He's got some amazing things to tell us about his cosmic interpretations. He's got a number of books, Beyond the Big Bang, and a number of other books he's been selling there, quantum kinetics and so forth. He's a PhD, he's president of the Starburst Foundation, an institute that conducts interdisciplinary research in physics, astronomy, geology, climatology, and systems theory. In 1986, he was the first to cast doubt on the Big Bang Theory. Of course, there are some questions about that. That is the Big Bang Theory. By showing that an alternative, non-expanding universe cosmology made a much better fit to distant data. The first to discover high concentrations of cosmic dust in Ice Age polar ice. The Violet made predictions about the entry of interstellar dust into the solar system 10 years before their confirmation in 1993 by the Ulysses spacecraft. His work has been published in the International Journal of General Systems, the Astrophysical Journal, monthly notices of the Royal Astronomical Society, and physics essays. It's my great pleasure of the last-minute speaker here, Paul Violet, from Schenectady, New York. Paul?
Thank you. I'm going to talk about a new approach to physics. Unfortunately, I won't have time to say too much about it because of lack of time, but I will spend a little more time talking about some of the predictions, some of the results that come out of this physics, particularly of interest here because they're dealing with non-conservation, energy non-conservation. which, as you know, one of the objections that physicists often bring up for these kinds of things is that they violate the first law of thermodynamics, namely that energy is always conserved. If you have energy, you can convert it to matter, and matter back to energy, but there's no net gain. And this physics that I've developed, it's a nonlinear system that's involved, and characteristically nonlinear systems, their aspect is that they'll tend to be non-conservative in case of energy. And these predictions came out of the theory and led me to check out the predictions in the astrophysical area. And I made some interesting discoveries, which I'll tell you about. Briefly, the theory involves a set of 5 equations, and that's it. From those 5 equations, you simulate them on the computer, and you get particle-like structures that produce fields that behave according to classical electrostatics, classical gravitation theory. This alone is quite astounding. The idea that you can create particle-like structures that will exhibit attractive forces, similar to what you find in physics. Not only that, these particles have no singularities at the center. This has been one of the problems. But before I get to that, I'll just show you these reactions here are, if you take those 5 equations and you diagram them, they're really not mathematical equations in the normal sense. They're kinetic equations. It's like recipes. You have A plus B goes to C plus D, this sort of thing. You would counter them in chemical kinetics. And when you string them all together, they produce this system of reactions. If you were to write out this in mathematical form, you would get 3 equations that are partial differential equations. And they are solved as a system. Now, the problem with that is that normal mathematics can't solve those precisely. They have to simulate them on the computer to really see how these behave. So work in this area has been done by Prigoghine's group, Brussels School. In fact, its model is similar to what they're working on. When you simulate these, now let me explain. The characteristic of this system, you can compare it to a nuclear reactor. Nuclear reactor is a nonlinear system. They use terminology there in nuclear physics, which I'll use here, the idea of the reactor being supercritical or subcritical. Now, when the reactor is supercritical, its power builds up. When it's subcritical, it's damping out. Depends on how they adjust the poison rods in the core. When they have a nuclear submarine, they want to bring it up to power, they pull the rods out, and the power goes up. It's in a supercritical state. Then they put the rods back in, dampen subcritical, and then they regulate it with the rods so that they're right at a threshold of marginal stability, they call it, where they're on the knife edge, right in between. Well, this system, this reaction system behaves in a similar manner in that when the reactions are supercritical, they form wave patterns. Here's a computer simulation in a one-dimensional reaction medium that was done by the Brussels group on a model similar to this one. We're using now this idea as a way of explaining how matter and energy came into being at the dawn of creation. The idea is that in supercritical condition, fluctuations can build up and grow into these wave patterns. Okay. And these are what we would use as representing particles of matter. This is sort of a cross-section viewed through the particle. Now, one of the problems with current physics models of subatomic particles is that the field at the center of the particle goes to infinity, whether it's gravitational field or electric field. It's due to this effect that they claim black holes are formed. Because as matter collapses, the theory is that it will collapse into itself infinitely and create a singularity. But a lot of physicists view this as a problem in that if the energy at the center of the particle is infinite, it disrupts the whole fabric of space-time to assume that there's these infinite energy points at every point that there's a particle. The beauty of this approach is that the value of the potential levels off. It also has wave characteristics. So you have, you resolve the wave-particle dualism. And I can go on and on about all these aspects. It's a very fruitful approach. But let me get to the cosmological predictions. One of the results that came out of this is that gravity is what determines whether these reactions that are generating matter and energy, and these are subquantum, we're postulating subquantum reactions, that set of equations. And by postulating that, you get these waves that resemble matter and energy when you simulate them. Now, one of the consequences of that is that gravity potential in this physics determines if the system is supercritical or subcritical. So if you're going to generate matter, you need to have a gravitational well develop sufficiently deep that the reaction medium is supercritical. And then you'll get the particles emerging. So the interesting result of this came about was that for this to develop a reasonable cosmology, you need to initially have space empty, which means space should have initially been subcritical. No matter and energy initially, just uniform. And that pockets, supercritical pockets, developed in which these particles could emerge. But if that's the case, then there would be places between these pockets of matter creation which would still be subcritical. And this is about what it would look like, sort of kind of like this. So let's say this is our galaxy here, and we have a gravitational well. And so in this region, let's say this dotted line is the critical threshold. That threshold in the case of the nuclear reactor where you're cruising with your submarine, steady power. Now here, it's a little counterintuitive because here, when gravity goes down, actually you're going supercritical. And in between here, it's subcritical. So the result that came out of this was that an energy wave, like a photon, if a photon was in this region, it was traveling in this subcritical region, its energy would become damped over time. In other words, redshifted. And the opposite would happen here. You'd have blue shifting in the galaxy. Well, I thought, my God, could this be a substitute for the cosmological redshift? At that time, I didn't know too much about astronomy. This is really what got me involved in researching this. I later found that actually this concept had been proposed years back. Actually, about the same time that Hubble published his results, Zwicky published a tired light model, it came to be called later. The idea that light loses its energy as it travels. And there had been, actually even before Zwicky, another physicist had proposed the idea. So it actually precedes the expanding universe hypothesis. As you know, expanding universe hypothesis is based on the idea that galaxies are receding from us, and that's what produces the redshift of their light due to a Doppler effect. So here was an other interpretation. The problem was at that time they didn't have a good explanation of what could cause spontaneous redshifting. And so it sort of became not emphasized. It was not in the spotlight, so not many people knew about it. Well, as it turned out, I compared both models, the expanding universe and the tired light, on cosmological data, and it turned out, to my surprise, that the tired light model fit the data better. I'll talk about that a little later, but first I want to get to one that's more of interest here, which is the blue shifting effect. Because what this means is that the energy of the photon increases over time. So think of it like, for people who are more into business here, think of the photon as capital, and you put it in the bank, and every year you're generating interest on your capital. So that's essentially what's happening to the photon energy. And the place you would see this the most, well, first of all, let me say that we're talking about very small amounts of energy non-conservation here. You take an iodine-stabilized neon laser in the laboratory, which is one of the better stabilized laser sources, and beam it over 100 meters and measure with spectrometer to see if there was any change of its frequency. And you can make some laboratory experiment to see how do the photons change their frequency or not. Well, let's say that you get a null result. Now, the thing is that all you're doing is getting an upper limit. In actual fact, the photons may be changing by a very small amount. It's just you can't measure it. The kind of change that we're talking about that's astrophysically important is 10 to the 8th to 10 to the 10th orders of magnitude smaller than that best laboratory experiment you could do with that particular kind of laser. So when physicists are saying about the first law of thermodynamics being violated and this and that, remember that it's for them to make such a precise extension, like into astronomy, of that law, it's a leap of induction. And they're sort of really becoming preachers at that point. There is an experiment which you could perform to test this, two variations which I'll talk about later, which might be actually able to detect if there is such a change. But now, the important thing is in stars, for example, here is where you have the greatest collection of photons. If you were going to see an effect astrophysically, you'd expect in celestial objects, because that's where you have the most collection of these photons. So take the sun, for example. If you can calculate its total amount of heat, and you say, let's make assumption that the rate of the photons are changing at a certain rate, you find that all the sun's radiation can be explained with a rate of change that's 10 to the 8th orders of magnitude lower than what you can measure in the laboratory. Well, I thought if this is true, that means that even the Earth should be generating heat, and maybe the heavy planets. And sure enough, you find that Jupiter, Saturn, Uranus, Neptune have internal heat sources. In other words, they're radiating an excess energy. If you see what they receive from the sun, there's actually more infrared coming out. In the past, these have been attributed to various processes. Like Jupiter, they say that's due to the heat resulted when the planet formed, primordial heat they call it, and over 4.5 million years it's been gradually cooling. In the case of Saturn, to get the kind of heat, for its size, it's producing more heat than Jupiter for its size, and so they either have to assume it was much younger, and therefore we see it hotter than it's supposed to be, or if it was formed the same time as Jupiter, we need some sort of other heating process. So astronomers have suggested various methods of producing heat, like crystallization of the helium and hydrogen in its core. In the case of Uranus and Neptune, they have the opposite problem. There, they need a cooling mechanism in order to make it fit this idea of Uranus and Neptune forming about the same time as the other planets. So the thing is that they need many different kinds of mechanisms to get a theory to explain why these planets are producing this heat. Well, the thought I had was, do these planets, what would happen if we plotted the masses and luminosities of these planets on what's known as the stellar mass-luminosity relation? And, okay, well, astrophysicists find that if you take a star's mass and its luminosity and you plot it on a graph, here we have mass along the bottom and luminosity here. This is log-log plot. That they, here are red dwarf stars. You find that they're forming a trend line. So the more massive a star is, the more luminosity it has. And here's the sun. Now, they find that right about 45% of the sun's mass, that the stars start forming a steeper trend line that goes up to the 4th power. Take mass to the 4th power, and that will be the luminosity for this upper trend line. For this lower trend line, which this is the red dwarf relation, it's called the lower main sequence, you take mass to the 2.76 power approximately. Well, here I extended the line down and plotted the planets, and sure enough, they lay along this line. Now, this was very interesting because what it means, if both the planets and the stars are on the same line, it suggests that there's a common process powering them. You can rule out primordial heat or crystallization heat and so on that they've been proposing for the planets because this just does not supply enough energy for the stars. It might light some of these stars for a few hundred or a few thousand years before they burn out. In the case of fusion, which they've been proposing for the stars, it just doesn't work, at least for hot fusion, for the planets due to the temperature. They say that below 0.08 solar masses, a star shouldn't have enough mass to ignite fusion. So what this shows is that neither of those explanations can adequately explain this common dependence, which I call the stellar mass-luminosity relation. If you actually go through the mathematics of figuring what would be the heat capacity of a star or planet, which is figured, you take the mass times its temperature and you make certain assumptions about its composition, you get a heat capacity per gram of material. You plug all these things in, you can figure the total heat content of the body. Now, remember, you also have to take into account gravity, because we're working with this physics. By the way, the name of the physics that I've developed is subquantum kinetics. This is the more technical book, goes in depth, and this is for the lay audience. It's more philosophical, brings in ancient myths. You find evidence that ancient myths encode this same science, which is another matter. I won't get into that, but that's also a very interesting aspect. But this gives a very nice general overview of this science. But as I mentioned, the gravity potential is important in determining the degree of supercriticality. So you have to also include the gravity of that the body is. As it's more massive, it's going to have a deeper gravity potential well. So this will also figure. And when you write out the calculations, you find that you predict a mass-luminosity relation about the same slope, which is very interesting. 10 years ago, I predicted that if a brown dwarf was found, that it should also be along this relation. And I published that 4 times. I published it in 1985, 1992, 1994, and earlier 95. And finally, in November, December, they made the announcement that they found a brown dwarf. So I took their measurements of the mass and luminosity, which they were giving an error box, really. They said the mass ranges between this and that, and the luminosity between this and that. And I plotted it, and here it is. with the upper left corner actually touching the relation. Of course, you're going to get some scatter in the data points. It's natural scatter here. But it would be interesting to see how close this will get as they refine their measurements. Now, with the Hubble telescope, they're able to get a good fix on the luminosity of the brown dwarf. They haven't announced it publicly. They're waiting for their paper to be published on that. To get a better fix on the mass, they have to observe the brown dwarf as it orbits the star, its primary star, because through observing the orbital motion, they can figure what its mass is. And since they just discovered it, I don't know, it was about a year ago, and it has 300-year time to make its orbit, it's going to take a while before they can see enough of its orbit to get a good fix on the mass. And as more brown dwarfs are discovered, I would expect that they would also hug along this relation. So far it looks pretty good, the results they've gotten so far. Now, what does this mean for collapsed objects? What happens when a star collapses? First of all, you wouldn't get a black hole with this physics for two reasons. One is that your gravitational energy does not go to infinity at the center of particles here, as I mentioned before. The other thing is, as the object collapses, its heat will go up, and its gravity potential will deepen. So you're going to be producing more genic energy. And you work out the equations, and you find that the energy per square meter or whatever is going up at the fourth power, whereas the gravitational force is going up by the square. So at some point, your energy out overpowers the collapse and brings it to a halt. So with this physics, it's possible to form very dense objects, let's say white dwarf densities. At the centers of white dwarfs, you can have billion tons per square centimeter or something, you know, almost to neutron star densities. So you could imagine very dense cores, stellar cores, that are radiating genic energy very intensely. Another aspect of this is that it resolves the solar neutrino problem. If you project this relation up here, it turns out it explains about 2/3 of the sun's energy, which is the amount that is, quote, missing. See, fusion reactions, if you assume that the sun is powered by fusion energy, you produce neutrinos as a byproduct. And so they built telescopes to observe these neutrinos, and they found that they don't get enough of them. They say, well, if for this amount of neutrinos, the sun should be putting out maybe about 1/3 of the energy, fusion energy is putting out. Actually, there have been 2 experiments. The Komiakandi experiment gives the missing amount as 0.54 solar luminosities. About 54% is missing. With the chlorine-37 experiment, about 75% is missing. So there you have a range of values. And this relation here, which naturally extends up, explains very nicely that missing amount. Another point is, why does this relation bend at this point? And my theory is that the reason that it bends is because that's where fusion energy kicks in. So that means that these stars here are, and the planets are powered by genic. I call this genic energy, spontaneously generated, this blue shifting of photons. Whereas the sun and other stars are powered by a combination. There's another graph you can look at, which is interesting, and this is called luminosity function. It's just sort of a population graph of stars. They look at the luminosity so that dimmer stars are over here and brighter stars here. Here's where our sun is. And there's just a chart of how many stars in each of these categories of luminosity. And the interesting thing is it's bimodal. And right about here, where this dip is around 45% of the sun's mass, where that mass-luminosity relation bends to a steeper slope. And I think this is what's happening, is that the fusion is kicking in right here, and a star that was formerly here, suddenly it might be producing 2 to 3 times the amount of energy it was producing before, because now fusion is adding in. So it's going to move from this point over here, because it's going to jump up in luminosity. So you're going to get stars leaving these categories going here, and it's going to produce a little hump, which is exactly what they find. Current models have trouble predicting why the slope of the mass-luminosity relation changes right at that point, at 45%. The best they're able to do is they would expect it to change around 35% of the sun's mass. So if you are able to add genic energy, a secondary source, you actually bring the theory close to observation. In the case of the Earth, genic energy can account for 73% of the Earth's heat flux. So the other remainder would be produced by radioactive decay. Should I wrap it up? Or do you have a question? Yeah.
To sort of wrap it up,
okay.
Tie it in, because it's an outstanding theory. It's quite amazing. It's obviously well thought out. What is the possible connection between genic energy in an astronomical sense and what we might be doing on tabletops? Can you see it?
Okay, here is what connection I see. First of all, we have here predictions that have been made, not only with a blue shifting, but in a red shifting. In both cases, the data is supporting the idea that photon energy is non-conservative. Be it a small, itsy-bitsy amount you couldn't normally observe in a laboratory. But the point is that if you can get the physicists away from that obstinate position that energy is conserved to the infinite decimal place, then you begin to at least open their minds a little to look at these tabletop systems. The other thing is that what this indicates, and it's written throughout the cosmos, is that the universe is nonlinear. Just looking at the behavior of photons, it indicates that there's the basis, what's creating physical form, is a nonlinear system. As we know with nonlinear systems, there's certain modes of behavior they have, which you put the system in a certain mode and you get all sorts of new properties that you didn't expect. That's why they have to model these on the computer. So what it means is that you could probably get much more energy change if the conditions of the system are right. And this is apparently what's being done on the benches. So the other aspect is the creation of the universe. You need some sort of process for creating energy out of nowhere, so to speak. Otherwise, the universe wouldn't be here. And a question that people often ask is, where does the energy come from? With this approach to physics, when you deal with the subquantum level, you're no longer dealing with energy as we know it. It's a different level. It's sort of like if you want to make a comparison, suppose the stock market fluctuations, the ups and downs are forming a photon. But they are not driven, although the money value is what you're charting, what's really driving that is people's desires. It's a psychological factor, maybe. And that's a different kind of animal. And so you're operating at a different level there. In this system, energy emerges. But the result, what produces it, the system that's producing it, is a system of process. It's a dynamic system, but it's not necessarily driven by energy as we know it. It's some other entity or whatever. Is there any questions? Yes?
I'd just like to make a comment that I really concur with vibrations of deuterium and hydrogen, which occur inside palladium and on nickel. Nonlinear processes. The Jahn-Teller effect is our kind of real-world example of dynamical symmetry breaking. What you drew in your presentation up here is a kind of gigantic Mexican hat. I drew the Mexican hat earlier, but you've got basically potential wells associated with full galaxies. Now we know that large-scale structure of the universe is highly nonlinear. There are these great walls. Margaret Geller at Harvard has discovered them. And indeed, there are gravitational potentials that exist on a very, very large scale. In fact, you'll see some of these in the movie that I'm talking about, because our heroine, actually, this is her field. She's addressing dark matter from this point of view also, and that was one of my questions about whether you thought a little bit about dark matter. But what you're suggesting here is kind of a cosmological analog of the type of potential wells that we're talking about on a molecular level, except it's occurring on a gravitational, cosmological basis. And I just find it very interesting.
This book explores the entire cosmology of subquantum kinetics and ties it in with ancient myth and lore and mysticism. It brings science, physics closer to mystical teachings. It's something we need.
Well, apart from mysticism, I mean, that's a whole separate thing, but I guess the question I have is, one of the really unsolved problems, the number one unsolved problem in cosmology today is the fact that over 90% of the universe is non-luminescent, is invisible, and supposedly is non-baryonic. Have you thought about that from the point of view?
The nice thing about this, it offers an alternative to the Big Bang Theory. So if you have a system like this in physics, which you don't need expansion because you've got a redshift predicted by it, you need some alternative. And what you find is that it predicts emergence, spontaneous emergence of matter, not in one event, but a process that goes on continuously. In other words, the sun is not going to stay the same mass. It's gradually going to grow. And you find that a star like a red dwarf, given enough time, will evolve into a sun-like star. It completely revises all of cosmology. And it fits the data very well.
Paul, thank you so much. As I must say, as a person who started out intending to be an astronomer, and I've been an amateur astronomer all my life, fascinated with it, I am very challenged by this. I think it's remarkable. Thank you for coming. Thank you for persuading me that you had something useful to tell us. And we'll try to end the day here with a little open session, some loose ends, and also to tell you that we're aiming to get out of this room so that some party can occur here. But there is another room that they tell us about. I don't know exactly where it is, but I'm sure they're going to tell us. Okay, it's much smaller, but it probably would hold most of us, on the order of 50 people. I don't suppose everyone's going to stay anyway. So that's housekeeping. I think what we're going to do is just open up this forum at this point to have people ask questions, bring up topics, bring up issues maybe for 15 minutes, and then we can unpack and get out of this room. Comments, criticisms, suggestions for the future, all in order here, even to the other speakers whom we've had before. Yeah. Thank you.
About the possible side effects of the technology that we might not understand.
Fair comment. I was playing devil's advocate a bit, to be honest, because I'm a great enthusiast for science. I'm sort of saying reluctant because you can't afford it. Okay, let's take a simple example. Let's take the detecting machine. They have to work pragmatically to improve the effect. Perhaps they've learned something about it. The other thing they have to do is to provide the basic commercial safeguards. Number one, they need to know about the life of the product. For example, does it eventually exhaust the water in some way? Right? Another one, and the strongest one of all, is what about the safety factor? Is the thing controlled? Is it fairly safe if it goes into thermal runaway? And secondly, is there any question of radiation or other possible harmful effects which must be searched for most rigorously? Having done that, you've satisfied the safety requirements, you've satisfied the control requirements, and you've satisfied the commercial requirements of reliability and so on and so forth. Can you think of any other requirement that is scientific test that is required as their work?
The problem is we don't know all of science.
Exactly.
There could be some particles, some energy that we don't understand.
This is true, but all one can do, and all one has ever been able to do, is to test it to the limit and rigorously test it to the limits of current knowledge.
The analogy, I might say, if I might interject that health issue, thought about this. Electromagnetic fields, there's still a controversy about it. Clearly there may be some biological health effects. Biological effects lead to health effects. I personally am persuaded that it's a worthy area of investigating those things. Now, when electromagnetic power was first introduced into the world at the end of the 19th century, no one thought much about those health effects. I suppose maybe some people did. I don't remember anything. I don't remember the history of talking about that. We're worried about people getting electrocuted. But now we're worrying about some subtle effects that may occur because these fields are varying, etc., etc. Maybe a similar thing will happen here. We can assure ourselves that there's no violent ionizing radiation. You can put detectors out and determine that. You can determine that there are no neutrons. But who's to say if there aren't zeta particles, or maybe some particles such as Dr. Violet?
Well, you didn't point out, Gene, that of course building these things as home power generators means you no longer have the electromagnetic fields to worry.
Well, you might, yeah. Although you might have them in the home. And by the way, one feeling that I have been having about this field is that it is so simple, quote, it may become so simple to do that once the, quote, secret of the beads, the infamous beads and the piles and the various other things are, you know, unleashed to the world, everybody's going to sort of try to make their own, much like you would make a solar collector. So for all practical purposes, it may be that after an initial, very intense commercial phase where certain key companies get a lot of money, it may be that everybody and his kid brother's going to be making these, including amateurs.
Well, in that regard, you see your magazine, and be it the near future or some point where, hey, here's something that you can build at home, and you can buy the beads or buy something like it.
I'd love to have an article like that on the cover. Do it yourself, cold fusion reactor, make your own beads, here's the materials, one thing from us, and heat your house and stop the oil trucks.
I take issue somewhat with that concept, as well as the whole idea of the electric utility will be absolutely disbanded with the commercial advent of cold fusion. And the point being, since we know how to drill wells, and I can go down to the corner store and buy a shovel, that doesn't mean every house on the block has a well. There is still a distribution system and so forth for water.
In New Hampshire, we mainly have wells.
Right. And there are circumstances, absolutely circumstances, where it would be more viable to have a home heater or a cold fusion system in each home. But there will also be a continued system, electrical system.
I doubt it. The reason being, when the wind blows, as it did recently, and there were thousands of people in New England without power, think of the advantage that one would have if one had their own electric generator in their basement or wherever, their apartment building, and had a backup ready to go in case it failed. And you never have to worry about the wind or the trees breaking and falling on power lines and repair of the lines. I think the chances that we will have an electric grid 25 years from now are approaching nil. That's my personal view.
Not mine.
Yeah.
Technically.
One thing I love about capitalism is the market decides.
Sure.
That's the way I would answer this question. The market will decide.
The market will decide. There'll be a combination of both, but I think the grid will wither. I can't imagine.
One other point I might add, I think this is coming at it not necessarily from a scientific point of view, but from a business development point of view. The perception by the public of this new technology may create an environment where you're going to face regulatory hurdles, as Chris has touched on, where is the wife of Peoria going to feel comfortable with her kids in the house with some kind of fusion reactor, if you want to call it that, power in the house, heating water, and things like that. Now,
we don't know.
You don't know.
Yeah, and so
it's a choice between.
You may want to call it
something else.
As Bruce said, something else, or.
Oh yeah. Well,
but we are going to face that.
Yeah, but we may know in a very short time one of two things. With a CD cell, you'll get such high powers, and you integrate it, you get huge energies. You either are going to see and identify the products within the next couple of years, maybe even 96. Okay, we'll find the products at those high power levels, integrated over time, or we will find that there's essentially no products. Okay. If the products turn out to be benign products, everyone will rejoice. Oh yes, now we know how it works, and everyone agrees that it's not dangerous. If we don't find the products, we'll say, gee, it dominantly ain't nuclear. It's something else, probably some kind of space energy, logenic energy, or some kind of energy. And who's going to worry about it? We have to take the risk.
Well, nuclear power is dangerous, so they could up by itself, or something like that.
It's a big social issue. There are many profound questions here of the market and health and safety, and most of these haven't even been seriously addressed, and I really hope that these can get addressed quick and soon rather than later when we have to deal with the issue. I think the issue is going to come up sooner than we think.
But this morning I don't cover this country, I saw the Boston Globe, and tens of thousands of homes in New England without power overnight, and one reporter said that apparently the 4 million gallons of heavy heating oil that's currently leaking in Point Judith,
Rhode Island,
is essentially uncontrollable. I mean, that is the other side of the coin, along with, what was it, $250 billion to get rid of nuclear waste. They can't sell the old nuclear power stations in the UK. They've sold all the others to private enterprise, but nobody will buy the nuclear power stations because there's no way the entire life cycle of a nuclear power plant, including getting rid of its waste, can ever be remotely economic. So they say.
Yeah.
While I believe that we're going to see the opportunity for home heating systems, at least as supplemental and someday as furnaces, complete independent units, I don't think that it's practical that we're going to see home power generation for a long time. And actually, if you look back historically, number one, people are very slow to make major changes, and adopting technology has really been, very difficult in ways where the infrastructure issues. Well, look at historically how long it takes things to come into play.
I disagree.
Well, no, I'll tell you why. Look at the windmill. Everyone thought that the electric windmill was going to do the same thing. And the funny thing is that the grid is the storage mechanism to buffer the excesses and allow you to take more when you need it, because we don't use power in a nice, continuous, uniform fashion.
The windmill,
we need it a lot at night and dinner time, and
The windmill, if I may say, with all due respect, I think is probably not the best example. People buy windmills for many reasons: aesthetics and psychology and everything, and as well as free energy. But I can't see how anyone would refuse spending, say, something less than $10,000 for a device. I imagine that's what a heater, unit with electric generator, to eliminate thousands of dollars per year of current costs.
But we have home nuclear and cogen systems today that are less than that have been on the market for 20 years. They have any, standalone nuclear reactors that are cogen that generate both heat and electricity.
Is it certified it's safe for domestic
Well,
use.
yeah, sure. And there's also cogen systems that produce electricity and heat, and they've been on the market for, you know, for 10 or 15 years. But the problem is that people don't want to spend money all up front like that.
But they're fuel. You have to buy the fuel.
You have to buy fuel.
But this is no fuel. Or
But you got a capital cost, though.
Yeah, like a television, a video recorder, a motor car.
I'd like to have a car that you don't have to fill up the gas tank.
The equipment in the house will wear out in 2 years.
That's right. That's
This will be eliminated.
Okay, yeah.
I have two questions. One is on the spheres. Now, has anyone tried, instead of using a spherical, like polystyrene or whatever it is, plastic or ceramic, something like zeolite? Zeolite has 1,000 times the porosity of the surface area, something like molecular cyst. Now, if they have tried that, is there a danger that the surface area is too great and the thing goes into explosive mode at that point?
In fact, there have been some unexplained explosions that we're still dealing with and we don't understand.
And it seems, it's interesting that the ones that you find that are the waste spheres that are sort of burnt out are the ones that are cracked. And could it be that the cracking is what promoted that?
No.
I mean, your comment about what's going to happen, why people would put these units in their homes. The gas companies and other companies are going to drop the prices of fuel.
Not that far.
Why not?
Because they can't get it out of the ground. There's a limit to how cheap they can make it.
You'd be surprised how far they'll go.
Well, it doesn't make a difference.
No,
They got the capital equipment to work.
there's going to be, with the political power behind the idea that we've got to get rid of CO2, whether or not there is a threat of global warming is not the point. People perceive there's a threat. When it becomes clear that we can avoid making CO2 in a large measure, there will be loud cries from many after the environmentalists wake up. They haven't woken up yet.
Some of them have.
Some of them have, not all of them. Most of them are asleep. But when they wake up and they say, oh my God, a solution to the CO2 problem, they're going to cry bloody murder, and Al Gore, when he finally wakes up, and he hasn't, will demand that we have this.
The other thing is that capital equipment all wears out in 20 years. That's what you have to remember. I have gone through 3 water heaters in my house.
20 years.
In 20 years. Well, that's all it matters. That's all.
Jim Griggs, the guy who knows heating systems, is going to talk.
Yeah.
I got a question for Dr. Johnson. In your relation that you mentioned earlier about the phase change of water, are you working on that now? Or are you writing?
Yes, with quantum energy.
Okay. In that phase change, I know that you mentioned that you're not sure of what the latent heat is now, but in those applications to where if that phase change takes place, should there be a change in the physical content of the water before and after you go through this process?
The
process in the water.
Yeah, the water, let's put it this way. First of all, when the process that you're creating occurs, the color itself may be associated, in my opinion, with the color of the water, the blue color, with the changes in local electronic structure, you know, a kind of luminescence, but not sonoluminescence. This is an intrinsic luminescence process or light scattering process. The water that you end up with, if it's in a truly closed system and not in contact with this vast heat bath, at least for a brief period of time, should be different, yes.
A brief period of time. So
yes, because I don't, well, if you could thermally isolate it, if you could isolate it, capture it, measure its properties, it should be different.
What about dumping it out on the ground and it's going to have a different latent heat? It's going to do something.
Well, if you dump it out on the ground, it's now in contact with the heat bath of the universe. It's going to revert.
Right, my understanding is
You're talking about changing the property, not removing, putting in some of the latent heat.
No, what I'm saying is that if, well, there are two things we can talk about. One is the cold fusion type experiment. I think we're talking about his experiment now, which is maybe, I'm just suggesting, not suggesting it is, indicating it is, it may be associated with the microstructure that you are creating essentially new phase of water through cavitation. All of this business about microcavitation may be connected with this. energetically, any microstructured water molecule should have a different energy, as Dr. Renaud will, I think, concur with, from bulk water. And it's that energy difference that may be accounting for what you're measuring in your experiments. I haven't followed the experiments in detail. I'm just simply throwing this out. One needs to then characterize the water in that particular state through a variety of techniques, spectroscopic, magnetic, and otherwise. Capture that water while it's in that state, while it's churning up, and characterize its short-range water. For example, there are state-of-the-art neutron diffraction measurements now being done on ordinary water. I don't know if it's possible to do it on your water. I mean, what happens when you stop the experiment going? Does the water retain its blue color? Does it goes back, right? So you have to characterize that water in the state that is this dynamical state that you're creating. This is science now again. Maybe Chris Tinsley would.
May I interrupt? I think what we're going to do is we're going to wrap things up right now because we really need to adjourn to either this other room, which we'll find out about. We have to move our stuff out of here. The camera crew has to put its equipment down. But I want to thank you very much for coming. And I want to say that if you want to have continued conversations, we will identify where the room is. If there's someone associated with the hotel hovering out there, ask them to tell us where the room is. Okay? Thank you for coming.